Okay, all right. Uh, okay, so any questions? I see, some questions in uh, chat box. Okay, can I, you guys can unmute and ask. So like I'll explain you and then we'll move to the next sessions. Okay, so there is something called drive strength. Okay, so what is this drive strength? So drive strength is basically, see, for example, if I've got a smaller inverter. Okay, say a smaller inverter. So it's basically say you have got an inverter. Okay, now you may have a device or the circuit which may have say a fan out. So you know what is the meaning of fan out, correct? So you may have a fan out of two, and you may have a fan out of four. You may have a fan out of 10. You may have a fan out of say 20. You may have a fan out of 50. Now, can we use the same, just one inverter, can we use the same thing to drive this much of load? Is it possible to drive such a big load? So it is basically you cannot use a simple inverter or say a lower drive strength inverter to drive a bigger load. So what we have is to meet the PPA requirements. Okay, what the libraries team have developed is there is something called drive strength. Okay, okay. So when I say drive strength, that means you will have multiple drive strengths. I'll just show you guys in the library itself so that you get an idea. I'm just connecting to my session. Okay, so now, okay, now this is what you see here. You know what you see. Okay, you see here now you have got say x0, x1, x2, x4, x8, x16, and x32. Okay, now you have got different inverters with the different sizes. So that means what x0 can drive smaller loads. So x0 can drive smaller loads. Okay, and then x32 can drive bigger loads. Okay, so that's the meaning. Okay, so the cells with different driving capabilities would is called multiple drive stands. It's basically we have multiple cells with the different capabilities of drive strength or the driving capabilities, and so that is something that we call it as a drive strength. Okay, uh, is that clear? Anyone else has questions?
Yes, sir. I have one doubt.
Hmm.
You are comparing drive strength with respect to PPA, power performance area. like
No, 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 I'm not comparing. Without these things, okay, a simple thing. Now, x0 will be smaller in size, okay? X0 will be smaller in size. Say, for example, now, if I have to show you, so x0 would be, say, something like this, okay? Now, x1 is going to be just same thing, same size, but x2 is going to be little bigger, okay? And then x4 is going to be, it's going to be little like this. So it is something like this. So it is the small drive strengths will be able to drive only smaller loads, and thus they will have a lesser area, okay? And they may have a little higher delay compared to your this one, because they will have a lesser driving capability. So now if you look at here, there are two things. One is area. So power is also kind of consumed less here because less number of transistors, okay?
yes.
So if you are actually have, if you have to hit 2 gigahertz design frequency, okay, now you need automatically multi drives, okay, or say drive strengths, and then multi VTs, and then there is something called multi channel libraries, okay.
Okay, sir.
Yeah.
Yeah, so just an example, Kumar. So here nothing but drives on is nothing but compared to each device, right? So like we'll be having thinner device or like lesser width, okay, and a bigger width. So
Um,
so I can just consider as thin man versus mm, a healthy man, like who can actually carry more load. So it is basically the same thing.
you can say like a man eating 2 idli and a man eating 10 idli.
Yeah, correct. So he can carry more load compared to this
Right,
guy.
right. So we will talk more on this all when we move to CMOS basics, because I will have to, see, I have not put the term called W by L at this point of time. So it's basically the width and the length of a MOS transistor. That is what defines this whole drive strengths. Okay, so how is going to be your device width, and then how is going to be your length. Now, which one actually, said, when you go high, when you say high drives, which one is width is going to vary or length is going to vary. So we will see all that in the CMOS topic, which is next topic. So right now we are in the first, session where, we are talking about the digital fundamentals. We will learn everything. So this, I'm just giving you guys questions so that like you try to spend some time, you get a chance, you explore, you come back with at least, not with zero, at least you come back with 30-40% of your, understanding. Now once you go through my session, it would be much more clear, as simple as that. That's the reason behind all this. Okay, any other questions? Okay, all right. So since there are no questions, I will move on. Okay, so there is one more question with respect to functional ECU.
Actually, sir, I believe functional ECU is nothing but the term we use the universal gates for spare cells. Is that right?
Yeah, right, right. But the functional ECO meaning, it's something that, you have implemented a design. Now it is ready for tape out in next 2 weeks or something. Now the change that goes in, that is something that we call it a functionality ECO. It is like kind of functional ECO we call it, where you are actually going and, changing your functionality or updating your functionality. Okay, so we will talk about all that in when we get into sign off stages, Mustafa. Is that okay? Okay, all right. All right. Okay, did you guys solve this problem? Did you guys solve this particular problems? I did not see anyone posting me an answer. Did you guys see solve this or no? Okay, so if not, then try to solve it in the upcoming classes. Okay. Okay, so we have discussed about NAND and NOR, based implementations. Okay. Okay, and we have also solved this particular thing. Okay. Now the next topic that I wanted to cover here is uh, so it is the Boolean theorems. So any kind of mathematics or any kind of problem solvings. Um, we usually have some or other the formulas or theorems that we follow so that like we can use them to simplify our the problem, or to optimize the problem or solve the problem. Okay, now it's the same thing here. So we have got say Boolean theorems which would actually be used. Say for example, you have a 1 and a, then output is going to be a. Now what is this meaning is, so you should understand that see, say this is A and say this is logic 1. Now what would be the output? It is going to be A. Okay, so ideally speaking, you can actually get rid of this and use the A directly here. Okay, think from optimization perspective. You don't need this, right? Say you look at from, say assume you have to write a tool. Now how do you look at this, or how do you write this? Say there is a logic which is something like this. Now how do you, uh, will you keep this cell, or you will get rid of this cell, or you will optimize it? Okay, so let me give you, say for example, now say if you have to implement this particular logic, what would be your optimized circuit? Do you really need two gates, or you can actually get rid of the first gate and just have A and B?
Yeah, get rid of first one.
So this whole thing you can actually get rid of it, and you can actually replace this particular thing with A. Okay, so these theorems are very much helpful when you wanted to optimize your circuit. Okay, okay, a simple thing now for your information. Okay, what are all the area optimization techniques that you can use in the tool, or say in your, say there are two parts to it. One is one is synthesis. Okay, the next one is during PNR, that is a place and route, that's nothing but your PD. Okay, so this is your next food for thought, or bites, or you can call it whatever it is. So if I wanted to target my area, say I have my chip that's supposed to be very small because I don't have much space. So now, say during synthesis, what are the different area optimization techniques that you can actually use, and then what are the different techniques that you can actually use in PNR during the PD. Okay, so let me just give you a simple thing for you guys to think. Okay, now say a simple thing here. See, you have got a flip flop. Okay, see, you have another flop. This just, there is nothing else here. So you have just got, say you have one here, and it is just goes as it is. Now say this goes to say some cell. Okay, say now this is basically clock. Okay, now if I ask you to, optimize the circuit, now what is that you would do? Okay, so this is one of the question. If you try to learn what are the different area optimization techniques, you would be able to, there is a term to it. There is a term to it. Okay, now this is one particular thing. Okay, now see there is another thing. Okay, you can actually look at. See, say there is a logic, okay, but this output is floating. This basically floating. Okay, you may have a circuit something like this. Okay, what is that you would like to do here? Okay, now say here there is a one which is kind of being propagated here, and now in this case, what is it you would do? Okay, so there are different optimization techniques, or the scenarios. So I want you to see. I'm sure this you may get something, but you may not get something, which I would actually explain you eventually in the when we progress. Okay, so these are all certain things that you would actually learn throughout the course. Okay, what is the term, and these are all the things that we actually focus in, kind of say in interviews. Say I might, let's say someone have, comes with, comes for an interview. If I'm the interviewer, say simple thing like, okay, tell me what are the, say I have a design which is literally an area critical, and so how, what are the different methods that you can actually think of optimizing your circuit in terms of area? Okay, so you guys can just try, these are all when you get time. Okay, and now when you think from that angle. Now, say simple right here, this one. What about this guy? Say now this is an OR gate. Correct. Say this is an AND form, and say look at this guy. You don't need an OR gate. I mean, it's AND gate here. Say these are all AND gate, right? Say for example, now you can just replace that AND gate. You don't need it. Only just use that out variable as it is. Now here you don't need anything even. Just get rid of that input and just keep that output as a zero. And see here, it is kind of, see, you have got an AND gate where you have to kind of so A. Now, what is this meaning is it's basically shorted, right? So both of them are driven by the same input. So why do you need this gate even? You just say A, you're done. Okay, and then you have got a complementary things. Okay, so that means what? So you have got to kind of complementary. Say this is A and this is A bar. Now, what will happen? One of them would be 1. Say, assume A is 1 and A bar is going to be obviously 0. So, you don't need this gate only. So, you can just get rid of it. Okay. Now, this, you may not understand the concept at this point of time, but remember, there is something called, say, A, Z, B, Z. Okay, now there is a path A to Z. There is a something called a timing arc. Now then there is something called B to Z. That is another timing arc. Now the question here is there a problem if you interchange both of these two? Is there a problem if you interchange these two in terms of functionality? So let's talk about in terms of functionality. Is there a problem when you replace this with swap these pins?
No issues, but like in terms of design, like when we connect like another gate to B, right? Like Z will be connected to B, and
No,
then like once we interchange, like LVS and all issues
no,
comes in,
no.
right? So
Kishan,
okay,
Kishan, my question is simple. Say, okay, let me give you. Say this is net A,
okay,
or say, okay, net B. Okay, so this is net B, which is driven by, say, an OR gate. Okay, now say this is actually a net A, which is driven by an AND gate. Okay, now simple. What is the next thing going to be when you do the swapping the pin? That means your net A will be here, net B will be here. As simple as that. That means this guy will be connected here and this guy will be connected. As simple as that. Okay. Okay.
yeah, correct.
So your
Mm,
LVS issues and all won't come into picture at this point of time. They won't happen.
okay, okay,
That doesn't matter at this point of time, if you ask me. So when you swap the pins, there's no issue. Okay. Now
okay.
the thing is, the assignment question for you is In terms of functionality, there is no issues. But what about in terms of delay? Okay, so I was just I'm just trying to understand, or ask you guys that. So A to Z. So look at, so delay of, say, A to Z and delay B to Z. Okay, case one and case two. How will it be same? Will they vary?
Same.
Guys, can you please go on mute? If you are sitting in a noisy background, please type your questions. Okay, so this is your assignment question. Take it as assignment question. Okay, because to answer this, okay, you should know the CMOS internals of AND gate, or say let's take it as an AND gate. Make our life easier. So take it as an AND gate. Doesn't matter. Okay. Now you know what? There is a one of the optimization technique. It's called pin swapping. Okay, this is one of the optimization techniques where, you know it is heavily used for, your PPA optimization. It is something we call it as a pin swapping. Now, to understand this, you should know the delay in this case and then delay in this case, A to Z and then B to Z. Then you would be able to, answer or understand how pin swapping helps you in terms of optimization. Got it? Okay. So we were talking about the Boolean theorems. Okay. And then now, see here, it is kind of this way. Again, this also you can actually collapse it. Say, for example, now, so how many AND gates you need? Say in AND gate itself. Okay, AND gate itself, there are two input AND gates, three input AND gate, and four input AND gate. Okay, now to implement this, what would be the two, how many number of two input AND gate is needed? To implement this, so how many input, how many two input AND gate is needed?
Two.
Okay, and in case if you have to use three input AND gate, if you are assume you are allowed to use three input AND gate, now how many such gates you are in need of? Okay, so it is basically one. Okay, now if I ask you, if I have a timing critical design, so not timing critical, say, okay, you can, let's say you have a, both timing critical and area critical. Now, would you prefer two input AND gate or would you prefer three input AND gate?
Three input AND gate.
Reason? Reason?
For timing critical, if you use two input means we have two instances, then delay will be more. We
Okay.
can reduce delay in three input AND gate. Other than that, area also we can reduce because one gate only required in three input AND gate.
Okay. Okay. So now, if you ask me, I would try to enable this or use this three input AND gate over the two input AND gate, because this two input AND gate would actually cost me two stages. Okay. The logic level of two. Okay. The logic level of two. So it is a kind of one after other serious way. Okay. And then they might be sitting, the placement of these things are matters and all of that. So it helps me to get rid of one levels of logic when you use three input. And okay, and also in terms of area, Okay, so your three input AND will have lesser area compared to your two plus two. Okay, two input and then one another two, basically one plus one kind of thing. So in terms of performance, I use this, I prefer this, and in terms of area, I prefer this, and in terms of power, I again prefer this. Okay. Okay, if I ask you guys, right, how many transistors would be there approximately? So that is another homework. So now in this case, say assume this is the equation that you want. I wanted to implement A into BC. Okay, this is the implementation that I wanted to do. Now using two input AND, okay, and three input AND. Okay, now how many transistors you will have when you know say case A and case B? What would be the transistor count? Okay, and now you can easily calculate how is your power consumption based on your number of transistors.
So just to understand, how is that two input AND gate requires two AND gates? So if it is two NAND gates, basically, right?
No, no, let's take it as an AND gate. No, A, B, C,
Okay.
right? Say this is B and say this is C and say and then this is going to be A. Correct.
Okay.
So this is going to be BC and
Okay.
then ABC. Simple, right?
Okay. So okay. So with the three inputs, you are taking two input NAND gate. Okay. Yeah, got it.
So this is one scenario. So this is going to be case A, and whereas in the case of B, I'm just going to use say three input AND gate. As simple as that. Okay, say A, B, C. Okay. Now the reason why I'm giving you guys all this work is you should think you are here to optimize your power part, right? It's not only power. Basically your overall design quality and everything. Okay. Okay. So
Kumar,
go ahead.
just a question. Which is more important actually here, timing or power or area? So how do we prioritize?
Okay, you want your left eye or you want your right eye or both of you are important? Okay, no, no,
Because
I know.
everything has a challenge in terms, right? Yeah.
No, no, I'm not, for your question, my question does not become an answer, but I want you to understand that, your performance, it depends actually. So if your block needs to be operating at 2 gigahertz, if it is a CPU, your performance matters. Power is kind of, second priority, but that is also, it is as good as high priority, as good as, your performance requirement. So to answer that, it is always we target your frequency because without hitting the frequency, you won't tape out. First of all, you cannot sell the chip to a customer.
Okay.
Say a simple, right? Let's say you have got a mobile which is operating, your mobile CPU is say 2.5 gigahertz. Now, say simple, right? Like, okay, let me just give you a quick thing. So,
So basically, it depends on frequency.
say simple. Now you are say OnePlus is the brand. Now they are actually trying to hit, target, competition here. So the maximum frequency at this moment is 2.5 gigahertz. Okay. Now OnePlus next version they wanted to come up with say 2.6 gigahertz. Now they have started advertising that this is going to be a bigger and in terms of everything and etc. But they have not revealed the spec. Now when the device is coming out, let's say now you are a company ABC, you are going to provide mobile chipset or mobile chip to OnePlus. Now, say you are actually closing your timing with 2.5G, but will he accept your chip with 2.5G?
No,
And let's say here actually say 10 watt power. Okay, now here it is at 2.6 gigahertz. Say he is actually giving, let's say it's kind of 11 watt power. Now, which one will aid in terms of marketing and pushing himself above in the competition?
Second one.
Exactly, because he will focus only this. Power is something that he will not, have you seen any time power becoming a criteria? And people say that, okay, I have to recharge. Power is not, the battery is draining heavily, and all that is post things. But he will be actually sell that, saying this is one of the fastest smartphone that you will ever have.
Okay.
So you understand, right? So to answer your question, it is all three are important, but our performance it depending on the device type, so where the application is, okay, your performance matters. Performance is kind of on the highest, high priority.
So with respect to frequency and timing, timing is nothing but frequency, is it?
Yeah, 1 by t is nothing but your frequency.
Okay. Okay. Got
1
it.
by t clock. So that's all we will
So,
discuss today.
yes. Okay.
Yeah.
Yeah. Thanks.
Yeah. Okay, any other questions before we see? You guys may not realize how these theorems are used and etc., but the reality is that they are, see, the tools that are developed, they are all kind of will have all these inbuilt things and etc. Okay. So that is why I say that you don't need to buy it or any of these things. So it's just that if you understand why these theorems are or the formulas or this hand I would say points or whatever that you can call it. See, so these are all the things that, see, from a textbook perspective, this looks kind of boring, but if you understand it in terms of, PPAs and, when you design a chip, what is that you are actually looking at and all that, you would actually never, feel that these are all kind of boring. Okay. Okay. All right. And then I would actually, share this with you guys in the email. Okay. So try to solve this, in your spare time. Okay. And so the next important thing that I wanted to cover is something called De Morgan's theorem. What is this De Morgan's theorem? So the De Morgan's theorem is nothing but it's basically your NAND gate. Okay. See your NAND gate. What is your NAND gate formula? What is your NAND gate formula? What is that NAND gate formula? Or the output equation? Say what is this going to be?
A dot B.
A dot B whole bar. Now this can be split into, when you solve this, what is this meaning is, so A bar plus B bar, isn't it? Now what is this meaning is, you have an inverter. Now that is an OR gate. Correct. So that is the basic thing. That is the basic thing that we will actually look at. So now why do we use this and where do we use this? So you may be able to optimize the area or the PPA again better. Now, so this is one formula where AB whole bar is equal to A bar plus, not XOR, A bar plus B bar. Okay. And now A plus B whole bar is equal to A bar dot B bar. Now this formula is known as De Morgan's law or De Morgan's theorem. And okay, now this is again going to help you optimizing the things. So any question here? Okay. So let's try to solve this. No, let's do a quick class work. So pick this particular thing. Let's try to solve this. Okay. I'll wait for your answer. Post your answers in the chat box. So yes, optimization means reducing gates, right? Yeah. So it is. See, it is not only reducing gates. So it is basically optimizing your whole delay from your start to end, and then you might be reducing your area, you might be downsizing the cells or choosing a different types of vt flavors. So optimization is basically your, say, simple, right? Like kind of, I can say, you see here, no, these three are same equivalent circuits. Now what is that you call it? Reducing the number of gates, and then number of nets, and then the size of these gates. See here, you have this three input NAND, but here there is no three input NAND. So it is something like this. So we are actually optimizing our logic, targeting your PPA. That's the basic thing. Okay. Yeah. Let's try to solve this now.
bias ఉంటుంది 100%.
Hello. Is there something?
మన నిమిషం వాళ్ళు వస్తారు యాక్చువల్లీ.
Let's solve this problem. Okay. So simple, right? Let's look at this way. Say now you have got this one. Now when you do this, a plus b plus c, this is going to be 1. Okay, and then plus, then a bar plus b plus c bar, and then this is going to be this. Now you solve this, so it is going to be a bar b bar c bar, and then plus you have got a double bar, which is a, and then b bar, and then say, okay, it is going to be c, just c. Okay, now you just take out b bar outside. Okay, now it is going to be a bar b bar plus, sorry, ac, a bar c bar, a bar c bar plus a c. So which means, what is this value? What would be this value?
0.
Okay, say for example, if this is 0 0,
1.
so this is going to be kind of say
Hmm?
1 1, so it is going to be 1. Now what if this is 0 and 1? So how you guys are saying this is actually 1? I'm just trying to ask you guys to verify. See, I understand you guys have said some answer. Now I just want you to verify that, is this is going to give you 1?
Yes, 1. It is in the form of a plus a bar.
Okay, so a plus. Okay, can you prove me this actually? So I always look at this way. Say for example, a c 0 0 0 1. Okay, 1 0 1 1. Okay, now what you are looking at is a bar c bar. That is a 1 category. What is the answer? In this case, it is going to be 1. Correct. A bar and c bar. Now in this case, a bar and c bar is going to be, what is the thing it is going to be? See, this is going to be, it's going to be what? See, this is going to be, see, A is 0. That means this is 1. And the C is 1. And this means this is going to be 0. So this is going to be 0. Okay. Now, what about this case? This is going to be again 0. And this is going to be, okay. Hold on. My bad. So AC plus A bar C bar plus AC. Okay. So let's look at this particular thing. Okay. Now, in this case, it is going to be say just 1, and in this case also it is going to be 1. Okay, that I am aware of it. Now, what about these two scenario? So this is going to be 0. Now, the other way also this is going to be 0. So it is going to be kind of 0 0, isn't it? Now, see what you guys are saying is, what is that formula, that something that you guys were saying?
A plus a bar.
Uh, A plus A bar. Isn't it? This is going to be always 1.
Yes.
But I don't see this, no? A plus A bar. How that is, I'm just trying to understand. See, I may not be knowing, or remembering this everything, but I'm just trying to, I want you guys to confirm that how did you guys come up with that B bar? What is that formula, or what is that you guys, many people have said that, but can you guys prove me that?
Like after second step, instead of taking B bar common, because I also don't remember.
Hmm.
So after say After your second step,
Hmm.
so you have taken B bar as common, right?
Okay, you
So
tell
like
me.
rather than that,
Hmm.
so I just multiplied each and everything with actually A bar into A and B bar into B bar and C bar into C. So that
No.
I've done, and then using that logic, I tried.
Okay, so what you're saying is you have just directly you have multiplied everything.
No, no. After second step, like A bar, B bar, and C bar plus A, B bar, C is there, right? Second step. After second
No,
step.
okay, let me just come to you this way. So same this say assume this is step one, this is step two, so this is step three.
Yeah.
Hmm.
Third
Now,
step, I've not taken common because this is.
okay, so tell me how would you
So
do
I
that?
just multiplied.
What is it you're trying to multiply
I
here?
just I just did A bar into A
A,
plus
yeah, open 1 minute. A bar
into A
into A.
plus B bar dot B bar.
I did not understand your concept.
Yeah, so that's not like I also don't remember, but like I tried in that way,
No,
and
there
then
is
I
nothing like a
took A bar out,
multiplication.
and then
No, hold on, wait.
okay, because
Uh,
that was a OR symbol, right? So I just multiplied it.
no,
Okay,
hold on. This is actually a plus.
okay.
Why are you multiplying this?
So because I use the bracket still, so I just multiplied. Okay,
No,
so that is wrong. Yeah.
that's the wrong thing, right? See, I'm just going in a systematic way, which you guys have done it, right? I'm just, guys. Why don't you guys give me? See, I'm just trying to understand. Like, you might be wrong. I'm not saying that there are many ways to solve it because you might have referred some different formulas, but prove me that whatever that you guys were saying, that's as simple as that. Okay, so I don't want to spend some time on this at this moment. We can actually work.
Sir, I got it.
Yeah, go ahead.
Hello.
I can hear you.
So, you taken the B bar is common, right?
Correct.
So, A bar dot C bar is equal to A plus C whole bar.
Hold on. Can
You
you
can
tell me?
write.
No, no, hold on. Yeah, that's what I'm just trying to write. Now, so you're deriving something from second step. Is that right?
No, from third step.
Okay. Third step, what is it you're trying to do here?
Yeah, B bar,
B bar,
bracket open.
bracket open.
Sure. Okay. A bar dot B bar, A bar dot C bar. I am writing A plus C whole bar.
Okay, so basically you're
It's
writing it like A plus C whole bar. Okay.
whole bar. Yeah.
Hmm.
Yeah.
Okay.
It's one
Hmm.
plus
Okay.
A plus C
Okay.
double bar.
Okay.
Yeah. It looks like A plus A bar, right? So then you can implement a 0001 1011. You will get all the ones.
Okay. Fine. So maybe I want you to verify this and tell me with certain things. That's a way. See, it's basically I'm looking at a foolproof answer that you guys justified your answer with the verification system. See, you might have just optimized it, but is it same as what your original logic? You understand, right? So,
Yes.
so
Yeah.
I want you to
For
supply
this, I am
the.
getting all ones.
Okay, so what you're saying is, say your A treat. Okay, so instead of this, it's like kind of just treat it like kind of say x equal to A plus C whole bar. Is that right?
Mm-hmm. Yes. And X bar equal to no.
That's
Yeah.
exactly what you're saying.
X bar equal to A plus C double bar. Yeah.
Isn't it? Do you understand this logic?
Yes.
How this AC is equal to A plus B double bar?
Okay. So
I'm just trying to understand. So is
yeah.
what is the way that you have tried getting it up? Because
So a plus c whole bar equal to
hmm, I have written here a bar individually dot c bar, right? This is what the outcome of the first thing, correct? Agree?
yes.
Now, when you solve this, isn't it going to be a plus c?
Oh, just a minute. Yes.
Yeah, no, maybe others. So there are many people here, but why are you guys are not trying or kind of you're stuck? What about others? Can you? Okay, if you guys have tried solving something, why don't you take a photo and share it in WhatsApp? I'm sure you have my WhatsApp detail, so I can actually check it out. So it's just that I'm just trying to find out, what is the logic behind your solving or your answer. You guys might be thinking, okay, so these are all the things. So I'm actually trying to verify. You guys are just giving answer, but how did you derive that answer is what my I wanted to check that, and I wanted to understand. Okay, did you follow the right steps? I'm not defining, or defining myself that okay, this is correct, but somehow I'm not convinced with this logic, this particular thing mainly. So I'm just trying to go, only figure out whether So the way he's trying to solve is like kind of AC equal to A plus B, A plus C double bar. But when I try to solve this, that does not come as a AC. It's kind of A plus C. Kishan, can you tell me again? Sorry. Is it?
Yeah. So like second component, whatever like Naveen mentioned,
Right,
right?
right. Yeah,
That
right.
A plus C double bar.
Uh,
So that should be A bar plus C bar single bar.
no, can you tell me this again? A bar plus.
Uh, Plus C bar.
Okay, now how do you derive that whatever that you are telling from this? A bar
Yeah.
plus
So I'll
C
just
bar, okay, and then
uh,
double bar.
uh,
Okay. So now,
uh.
okay, now if I try to take that as a thing, now will it be giving me this A plus A bar B or
No, no,
something?
no. Yeah, yeah. That wrong. F is equal to B bar is actually the wrong answer. But whatever the equation AC is, right? So
Hmm.
you usually we write AC is equal to AC double bar.
Yeah.
Okay, AC is nothing but AC double bar, right?
Yeah. Right. Exactly.
So from there we have to like derive it. So like I just took like AC is equal to AC double bar and then derived this equation. So I just converted from AND to like OR gate and then was trying to get the logic. But yeah, so the final answer would be B bar into A plus C bar plus A bar plus C bar into the whole bar. So it is a bit complex equation only. It is not straightforward. So F is equal to B bar is not the right answer.
It is not that it's simple. And what gate it is this? If you guys look at what gate is this, it is a X now.
Yes. X nor, yeah.
Okay. So X nor cannot become a one just like that. They are different altogether. Okay. So these are all the basic things where you might tend to okay, this is how it is, no, but the way I'm just giving you is yes, you can have it, but verify it before putting it out. That's my point of view. Now that is exactly what we do in industry also. You are basically now say you have just optimized a circuit. I gave a circuit. Now you optimized it, and you are saying that okay, this is the answer. This is how your output. Now take it and go. Now, who are you guaranteeing that it is the input circuit that I gave and your output circuit are they same? that verification process that you have to basically validate that with supplying zeros and ones. So that is the way I look at any work that you give me something. I ensure that you might complete it, but is you have done it in a right way or not. That's the basic thing that I actually look at. Okay. Okay, all right. Try to solve these things also. I'll share it in the email. You guys can go through that. Or anyway, you'll have these videos uploaded, all right, in YouTube. You can actually go over. All right. Okay, so the next thing, any questions before we move to the next things? Any questions before we move to the next topic, which is Karnaugh map? And then we have Mux. Okay. Now, first of all, if I have to ask you, do you remember all those formulas, the Boolean formulas that we discussed? Would you be able to remember everything? It is impossible. It's not easy unless you have some reference paper or something. Okay. Now, the thing is, the next easy method to optimize that is basically something that we call it like kind of, Karnaugh map. And they are actually used to optimize the same circuit. Okay. Now, here, it is something that, we have got one, two, three, four column, four, field. Okay. So it is basically 2 to the power n kind of thing. Okay. Now, that means say your A, B, 0 and 1. Now the first thing is say it's 0, 0 and then 0, 1 and then 1, 0 and then 1, 1. Okay. Now, uh, if you have multiple variables, okay, you know what? So you need say two variable, you need four field, okay, two rows and two columns. And when you have three variables, see you might remember the naming of this matters. Okay, the naming of this matters. You know what I usually do it like I kind of take it like A and then BC, so that like kind of you can actually go this way. It is kind of I always feel that way. But now if you are having it in a different way, then it is going to be different. The way you need to understand how you are to do it. So it is going to be kind of say 0, 0, 0, 1. So this is going to be say 0. Okay, and then 2, 3. And remember, it is kind of here it is a 1, 1. Okay, and then here it is 1, 0. Now, do you see something that between these things? What is it you are noticing here? See here. What is it you are noticing here? Between two things, right? What is that you are noticing? How many variables are
One bit
changing?
change.
There is
One
only
bit
one
change.
bit change. So Karnaugh map actually, help, the way it is built or implemented, or the way they came up is one bit changes when you move from one box to another box. That's the basic thing. Now see here, it is a 0, 0. Now 0, 1. Now if you are actually going to a next one, it is going to be 1, 1. Okay, it is going to be 1, 1. And then it is a 1, 0. Now if you look at in the binary, okay, now look at this. See here 0, 0, 0, 1. It is perfect. Now what about this guy? How many bits are changing?
So it's
Between these two, there is only one bit. Now what about these two? Two bits. Okay. And then what about these two? Again one bit. Now what about these two? So the way the Karnaugh map is implemented is it is a kind of they actually change only one bit at a time. Okay, they change only one bit at a time. Okay, that is the meaning. That is how it is actually helping us. Okay, now look at this. Say simple. The way we look at is you get your equation. So f is equal to x something that you are getting the equation. Now this equation is expanded in terms of truth table, and now this truth table is then filled in this Karnaugh map, and then we actually solve it, and then we actually group these ones. You know what? The way we group is, so 2 to the power n, the number of inputs. So for example, in this case 2. Okay, 2 into 2, that means so basically 4 in 4 ones. That is basically, if you have all the 4 ones, then the output is basically 1. Okay, now that is one thing. Now second is, now 2 to the power 1, so you need to minus it, so then it is going to be just say 2. Now you see here, so you are kind of grouping each of them, okay, in a kind of pair of 2. Now remember, when you are doing this, at least one number should be unpaired. At least one number should be unpaired. Say there is a one thing which is kind of paired. Okay, now say simple. If you guys look at it, when you are grouping, there has to be at least one number which is not grouped. Then only that grouping is valid. Now say in this case, you know what? See here, it is the way we group is, see, this is actually 4. This kind of, see, between this and this, there are only 1 bit changes. So you can actually, it is a kind of, say, take a paper and roll it, okay, and take a paper and join both the edges. So it will be like kind of circular fashion. So that is how it actually forms. So 2 bit changes. So now it is kind of, say, 4-bit grouping. And this also kind of, say, 4-bit grouping. Okay, so it is a 4 times 1. Now, the next is, see here, you can actually have only one is, this one is not grouped. You know what? Now this is actually grouped. Now, is there anything that is ungrouped? Is there anything that is ungrouped? But now let me tell you, you are not supposed to go and do extra grouping of this only. There is a two ones which are kind of, it's possible to group, but I don't want you to group it. Okay, I don't want you to group it, because when you are grouping, at least one number should be ungrouped before you go and say that is a valid group. Okay, so that's a basic thing. Now let's go back to our basics. So this one group, which is kind of, say, this is basically, say, b is constant here, so the outcome of this group is b. Okay, and then say here in this case a is constant, and whereas b and b is 0 and 1, it is kind of, say, only a. So the outcome of this particular thing, say a plus b, okay, is basically this. That's the best thing. Now let's talk about this. So this is the given spec. Okay, this is the spec. Now what is that you're actually doing? You're basically implementing the truth table. All right, now you're actually going and filling all that. Okay, now assume, what is that, 8 times, ones, is there 8 ones? Next is there are there 4 times ones that you can group, and is there 2 times ones that you can actually group, and there are 1 time ones. Now in this case, 8 times 1 is possible, not possible, not, there are no 8 ones, so that is ruled out, and 4 times ones, yes. So this, along with this is actually basically 8 times 1, which is very much possible. And this, okay, now we are done with this. Now how many of them are ungrouped? There is only one, only one is left over. So now I'm just using a 2 cross 1, 2 time, 2 groups, 2 ones that I'm actually grouping. Now that is basically done now. Okay, now what does this meaning is, now look at this. So this 4 ones giving me, what it is giving me. So the C is gone because 0 and 1, and then this 0 0, and then 1 0. So that means the 4 times 1 gives me a B0, sorry, B bar. Okay, B bar, and then plus this 2 group, okay, gives me, say here, it is kind of A C bar. Okay, A C bar. Now, so this is how your Karnaugh map is implemented. Okay, So any question here? So how the Karnaugh map we solve it, and remember the advantage here is between the boxes or the fields there is only one bit changes. Okay. Uh, I can actually share some homeworks for you guys to practice. Now, remember, so I have not gone into in depth of it. Where this is actually this one, and then plus don't care. So sometimes you can actually have a don't care. Now, say for example, you may have a say don't care meaning say we call it like kind of X. So you can actually use them for your optimization, considering they may be a positive, or they can be treated as a one also. Now in this case, you know what? If assume there is something kind of don't text, don't bother or don't care. Now, in that case, instead of this two grouping, what I could have done is I could have actually went and grouped this with all this four, and then what would be the case here? It would be just A. So the final outcome could have been A plus B bar. Okay. So there are ways, there are the problems that could you may have it. So I can share some problems with you guys. So you can just go over. All right. Okay. All right. So anyone has a doubt in Karnaugh map? Okay, so the next basic building blocks in digital is basically half adders and full adders. So they are basically used to add, So see, remember, right? So when you say CPU, it performs all the kind of operations. Okay, so it contains ALU and all the kind of things. Okay, so arithmetic logic in it. So now when you say ALU, it would do addition, subtraction, okay, and then multiplication, and then division, okay, and there are many more operations, right? So shift left, shift right, and then there are many more operations it can actually do. So basically the adders are one of the basic building blocks for any designs, okay, and then they would be used a number of times. If you look at, right, in adders itself you have a different types of adders. Say for example, if you are kind of need of efficient adder, that you are kind of hitting high frequencies, so you might pick a different types of adder, and then let's say you are looking at area. Now you might pick a different types of adder. So that's why we say when you are doing optimization, you should set the settings where the tool would pick which is the right thing that it has to do and all that. Okay, so let's talk about the basic adders. So when you say adder, half adder, there is see, there are two inputs. Remember that just X and Y, but there are two outputs, which could be like kind of one is sum, and then there is something another thing called a carry. Okay. So now here, if you look at when you add 0, 0, the sum is 0, carry is 0, and when you add 0 and 1, sum is 1, carry is 0, and when you add 1 and 0, so the sum is 1, carry is 0, and when you add 1 and 1, okay, that means it is basically 2. So your sum is 0 and your carry is basically 1. Okay, so this is how the addition actually happens. Now, so this is your becomes your truth table. Now solve the truth table the way we have done the Karnaugh map. Okay, now solve it. Say kind of your output C. It is basically now applying this in the Karnaugh map. It is going to be say XY. Now sum means look at this. Say, now you have got two ones. Now what gate that you need to use? Say this is XOR gate. When you solve this, it becomes XOR gate. Okay, so now you see here this is a AND gate, and say this is XOR gate. Okay, now this is basically off adder where we have only two inputs and we don't take any carry ins. Now there is another thing that is called full adder. Now full adder means there are two inputs which are X and Y, but there is another thing called carry in. Okay, now here there is a sum and then carry of that particular stage. All right. So when you try to solve, you get something like kind of carry. This is the equations, and then your sum. This is going to be your equation. Okay. So when you draw the gate level circuit, this is going to be your gate level circuit. Okay. So you should actually go and try to understand the very level, basic level, and etc. Okay, so now using this full adder, I'm not sure if I gave you guys the homework. 4-bit adder. Okay, there are different types of adder. Okay, list all the different types of adder and how they are implemented. List different types of 4-bit adders, and then say in terms of PPA, which one would you choose? I want you to justify. See, you might, all these days you might be just writing, some answers and do that. But now, what matters is once you're trying to get into industry, what matters is your justification. Okay, so I'm going to use. I'm given a chance, given a chance or given all these adders, I would pick X adder or say this particular adder because it gives me advantage of say power and area or say power and performance. Okay, so that is something that I want you to have start learning that. You need to write your conclusion or your suggestion. Okay, say once you are in industry you would start contributing something. Now some people might ask, okay, can you compare these two runs and tell me which one looks good in terms of what? Okay, so all that matters. So I want you guys to list different types of 4-bit adders and then tell me uh, which is good and for what purpose. Say for example, power in terms of performance, I am looking at very efficient adder. Say I want to hit 3 gigahertz, then which adder will help me? So you need to look at what is the logic depth. Okay, how many registers are there, and so everything that you need to look at. Okay, all right. Okay, we'll stop here because I want to spend some good amount of time because it matters. So I want you guys to take this as a homework. Okay, these are all the things that you guys can actually take it as a homework. Where you guys try going through the basics. A lot of materials available in the web. You guys can just go through it and then understand. See, the reason why I'm you might question me, Kumar, is that these needed for you to be a PD engineer? See, you are actually working with the gate level designs. So you having a knowledge, you are not going to design, but someone else is designing and giving it to you. Now, the thing that I want to do here is do you understand the circuit? Let's say tomorrow you need to build, or you are not meeting your requirements, or you are not able to hit your targets, frequency target. Now, what is that you suggest to someone who's designing? So you having an idea of all these basics is basically it's something like kind of ABC for you to it's kind of an ABC before you write essays or do something articles and etc. So that is why I'm just trying to spend, otherwise I can actually get started with PD activities. Okay, and in case if you guys want to know like where you can refer, so my previous videos or previous batch videos are captured, posted in YouTube. You guys can go over that and you can actually come, be prepared, and then come, you can actually understand much better. Okay, but I know that I'm going slow, but I would not be this slow once we get started the actual topics and all. But because you guys are just, many of you are kind of coming from industry and then coming after a break, and you need to start getting into the learning mode, which I'm just giving first a few weeks. But let me tell you, once you pick up the phase, these are all half an hour topics. Okay, just letting you know how how it would be. So try to go through it before we get started on our actual topics. Okay, I think that's all I wanted to cover, and let me know if you guys have any answer. I can help you. If not, then we are done for the day.